In this video, we're going to start looking at functional groups and reactivity. So, functional groups and reactivity. So, just taking a closer look at a few of the functional groups that we had talked about in the first video of this module. So remember, the functional group determines the molecule's properties, both physical and chemical. So the functional group determines the molecule's properties. Both physical, which we've looked at, right? Alcohols can form hydrogen bonds, so they have London dispersion forces, dipole-dipole forces, and hydrogen bonds, which affects the boiling point and the melting point. Also affects the solubility. Do you need to take into consideration the ratio of nonpolar to polar portions, however, when doing that? So both physical. And then in this section, we're going to look a little bit about our chemical properties, so reactivity, how it's going to affect whether or not it's going to react with a certain molecule, other molecule or not. So the functional group determines the molecule's properties, both physical and chemical. So an atom, a couple rules for us. Our first one, a functional group. Let's actually just leave that. An electronegative heteroatom. I don't know if I've used that term yet. I'll define that here in a second. So examples, nitrogen, oxygen, halogens make the carbon that it's bonded to electrophilic. So a heteroatom is just an atom other than carbon or hydrogen. So nitrogen, oxygen, halogen, sulfur, phosphorus, all of those would be considered heteroatoms. So again, a heteroatom is just an atom in an organic molecule that's not carbon or hydrogen. So if I was to bond something electronegative to carbon, it makes a dipole. So an example, if I was to look at an alkyl halide, right, my sp3 hybridized carbon bonded to that halogen. Oop, I put a negative on this one. Chlorine's electronegative, so it gets a partial negative, right? I'm pulling electrons away. So that makes that carbon electrophilic. Right, remember, let's do a little reminder. We introduced these terms in the last chapter. If something was electrophilic or an electrophile, however you want to say it, this is our electron poor site. Something that is nucleophilic or our nucleophile, right? This is our electron rich site. So my carbon in this case, right, is partial positive, making it electron poor, right? Electrophiles are either positive or partial positive. So anytime I go and bond an electronegative heteroatom to carbon, right, we can do the same thing with an alcohol functional group. Because that oxygen is more electronegative than that carbon, it's making that carbon electron poor. It's making that carbon electrophilic. Right, that carbon right there, it's supposed to be an arrow, is electrophilic. Right, it's partial positive, it's electron poor. And then the same thing with that carbon, electrophilic. So alcohols, alkyl halides, right? They end up with an electrophilic carbon. our second trend, a lone pair of electrons, or a non-bonding pair, whatever term you like better, on a heteroatom again, so an atom that's not carbon or hydrogen. We are going to exclude halogens from this though. Halogens don't generally fall under this rule. Remember, X is our abbreviation for halogens. So a lone pair on a heteroatom makes it nucleophilic. Our nucleophilic sites, or our nucleophile, right, is our electron-rich site. So if I wanted to look at an ether functional group, right, I have some lone pairs on that oxygen. Those lone pairs are nucleophilic. I could look at an amine functional group. Let's put a hydrogen and another group. So I have a secondary amine. I have a lone pair on that heteroatom. That makes that heteroatom nucleophilic. Remember, these are my electron sources, right? My electron-rich site. If I'm going to draw my curved arrows when I have a reaction, it goes from the source. That's going to be the lone pair in this case. Another trend we can see, and that's pi electrons. So pi electrons are the electrons in pi bonds. Are nucleophilic. And again, nucleophiles are electron sources, right? There are electron-rich sites, and we already know from resonance that lone pairs in pi electrons are good electron sources. So nucleophilic again, right? Our electron-rich site. So if I was to draw an alkene, right, I have some pi electrons, or an alkyne. Remember, these guys are sp hybridized, so linear. There's 4 carbons there. That would be considered nucleophilic. So another little reminder for us. Our nucleophile reacts with the electrophile. And this is for polar reactions. We're actually in chapter 6 going to look at other types of reactions where this isn't necessarily true. But the bulk and pretty much all of the reactions that you're going to be responsible for, except for the couple examples that I give you in chapter 6 of things that aren't polar, are going to be polar. So these are for polar reactions, polar mechanisms. You don't actually do any, besides the example ones, reactions that are not polar until you get to 236. The bulk, and you only do a couple. I would say probably 95%. I don't think that's exaggerating. It might actually be even conservative of the reactions that we're going to do are polar. So in a polar reaction, we have an electron-rich site reacting with an electron-poor site. So our nucleophile reacts with the electrophile. So kind of an example, if I wanted to take this alkene, right, it's nucleophilic, right? I have pi electrons, and then I'll just use E+ for a generic electrophile. Remember, our arrows always go from the nucleophile to the electrophile, right? From the source to the receptor. So those guys could react with each other, and I could form a bond between one of those 2 carbons and that electrophile. I could do an example with an alkyl halide. We'll just use a generic halogen. Remember, as soon as I put that on there, that makes this carbon electrophilic, right? Because it's partial positive because of that bond dipole. So if I had some generic nucleophile, it could react with that carbon, because that carbon is electron poor. That carbon would have too many bonds right now because it already has 2 hydrogen on it, right? I didn't give it a formal charge, it has a partial charge, but that has to do with the electronegativity difference. So I would generally end up breaking that bond, right? That bond is weaker than the bond between carbon and hydrogen, right? Because that's considered non-polar. If I have a polar bond, it's going to be easier to break it. So that's the one we're going to break when we add to it. So kind of another type of example, I'm going to give you a set of molecules, so two different things, and we want to know, will they react? And this is just based on electron density. So is one electrophilic, is the other nucleophilic? If that's the case, then yes, they will react. If they're both nucleophilic, then no, right? Something that's negative is not going to react with something else that's negative, or electron rich with something that's electron rich. If they're both electrophilic, then they're not going to react. We need one to be electrophilic and one to be nucleophilic, right? One to be electron poor, one to be electron rich. So will the following react? And again, this is just based on electron density. Just because you have a nucleophile and an electrophile doesn't mean they will necessarily react. We're just not there yet. So right now we're just identifying electron rich and electron poor sites. So based only on electron density. Essentially, it's not as simple as we're making it here. But again, we're practicing. Do I have an electron rich and an electron poor site? So our first example. So this one, and then let's have a hydroxide ion. And I'm not going to always put these lone pairs on here. So please, actually let's do, well, they're on there now. I was going to get rid of them and then put them on together, but you know where they are because I just did it. But do try to get in the habit. Like I'm not putting them on bromine, but there are 3 lone pairs on there. So just be careful. I'm not going to always put them on there, but you do need to know that they're there, right? If I didn't put them on there, would you recognize hydroxide as being nucleophilic? Hopefully you would, because you would see that negative charge on the oxygen, and you would know it has to have 3 lone pairs on it. I started to erase the lone pairs on bromine, but I'm going to put them back because bromine is a heteroatom. It has lone pairs on it, but if we go back up to our trends, we excluded halogens from this. So those lone pairs on halogens are not going to be considered nucleophilic. The lone pairs on oxygen, however, are. So if we go back down, this is nucleophilic. I have a lone pair on a heteroatom that's not a halogen. I have a heteroatom bonded to a carbon, making that carbon electrophilic. So will these react? Yes, right? I have 1 electron rich site, I have 1 electron poor site. Another one for us. So will those react? I want you guys to think through this one yourself first. And then if you have to pause to think about it a little bit, by all means, and then just hit start again. Okay, so nucleophile, right? Pi electrons make it nucleophilic. And then chlorine with a negative charge, there's nothing electron poor about that. It does have lone pairs on it, and I said lone pairs on halogens you can exclude as being nucleophilic, but the fact that it's a negatively charged ion actually still makes it nucleophilic. And even if you don't recognize it as a nucleophile, it's definitely not electrophilic, right? It's not electron poor. We could even just say it that way. It's not even a very good nucleophile, so let's just say not an electrophile. So our answer to this one is no. If I have that alkene and a chloride ion, those guys are not going to react with each other. one more for us. So I have a ketone and I have an alcohol. So again, please try to reason through this one a little bit on your own and then come back. So hopefully you guys did that. I would put the lone pairs on. I didn't include them for you, so hopefully you listened to my advice and you did that if you needed to. So you can look at this one two different ways. I'm going to say that the lone pair on this oxygen makes this nucleophilic. You could say that the lone pair on this oxygen makes it nucleophilic also, and you'd be correct. But I do have a partial positive carbon, so I'm going to make this my electrophilic atom. You could do the opposite because I also have, let's just do it again. So yes, I have one of each. Let's write that down first. And then I'm going to look at it the other way that you could do it. So I'm just going to redraw the same thing. So I do have lone pairs on my ketone oxygen. So we could say that makes that nucleophilic, right? It falls in our guidelines that I gave you. And then on my alcohol, I do have that oxygen bonded to carbon, making that atom electrophilic, and we would still say yes. So whichever one you make the electrophile and the nucleophile, because each can be either, if that is the right wording, you're going to get yes as your answer.